In this tutorial, we're going to talk about expected value. It's a really interesting topic. Statisticians and mathematicians do all sorts of really interesting things with expected value, but it can get complicated, so we're going to stick with the basics. And we're going to ask a very simple question. What does the mean mean? You might think that's too simple of a question. I know what the mean means. And when I'm done, you're probably going to think, you made that way too complicated. But I hope that you can stick with me, and you'll see that by taking this roundabout way of answering the question, what does the mean mean, we'll be able to get a deeper understanding of other statistics like variance and skew and kurtosis. So let's start with what we already know. Suppose we have a sample of 25 numbers, and it looks like this. So we have 1 3, 1 4, 2 6s, 7 7s, and so forth. If we wanted to calculate the mean, we could just do it like this. This x bar means the mean of x. We get a 3, a 4, a 6, another 6, all 7 7s, and add up all these numbers like this, and then divide by the number of numbers. There are 25 numbers here, so I divide, and I would get my sample mean. So fairly simple. But look, here's we can think of it a different way. We can take the number of 3s times 3, the number of 4s times 4. We had 2 6s, so 2 times 6. We have 7 7s, so 7 times 7. 8 8s, so 8 times 8. 4 9s, 4 times 9. 2 10s, 2 times 10. Or we could do it like this. We can get a table, and so in this column we have the numbers themselves, so 3 through 10 corresponds to 3 through 10. And then in this column, the frequency of x is how many 3s? We have 1 3. How many 4s? We have 1 4. How many 5s? We don't have any. See, we have a gap there, so we have 0. How many 6s? We have 2, and so forth. Let's add up all these numbers in the F column. 25. Look at that. It's the same number as we have here. So if we add up all the frequencies, what we get is the sample size. Now, let's do what we did here, which is we're going to multiply the number times the frequency, the number times the frequency, the number times the frequency, and put them all in this column here. So 3 times 1 is 1, 4 times 1 is 4. 5 times 0 is 0, and we go all the way down, like so. What we're going to do is then sum all of these, and we get 188. Now we're going to do something a little different. We're going to take this column here, and we're going to divide by n. N is the number of numbers, or the sample size. And we can do this, because imagine if we were to separate this out, we could say 1 times 3 divided by 25, plus 1 times 4 divided by 25, 2 times 6 divided by 25, and it would still work out. It would still be our sample mean. The calculation would be correct. So 3 divided by 25, 4 divided by 25, 0 divided by 25, 12 divided by 25, and so forth. Let's calculate that out into decimals, and we would get this. If we add all of these up together, we'll get this. And look at that. The same as our sample mean. That is, the sum of this column equals the mean. What is that column? Well, f of x divided by n is the probability or proportion of x. So we could rename this column as x times the proportion of x. And we can put it in a formula like so. The sample mean equals the sum of all x's times the probabilities of those x's, and gives us the sample mean. That is, it's a weighted sum, weighted by the probability. So that's another way of thinking about what is the mean. It's a kind of weighted probability, or the sum of the weighted probabilities. Now, if we were thinking of this variable as a population instead of a sample, we could say that the population mean equals the sum of the values by the probabilities. When we get the same value, the calculation for sample mean and population mean is the same, but conceptually it's different. We're saying this is all there is, whereas in a sample it's a subset of all that there is. This leads us to a concept called the expected value. When we're talking about populations, we can say that the expected value of x is the population mean of x. That is the long-term average. If we were to keep sampling, on average, what score would we get? For discrete variables only, the expected value of x equals this formula. But what about continuous variables? Well, this doesn't exactly work out. We actually have to think about it in a slightly different way. But before I get there, I want to mention that expected value is a much broader concept than just the mean. So the expected value doesn't just mean population mean. It means a bunch of other things. It's a broader concept. To give a taste of what we mean by this, let's play a game of chance. You're going to roll 2 dice and add them together. If the sum is even, you win $9. If the sum is odd, you give me $10. Do you want to play? Should you play? Is this a good game or a bad game? Your intuition is probably anytime someone asks you to play a game of chance and money's involved, it's probably a bad game. You're probably going to lose. In this case, your intuition is right. This is a bad game. But let's figure out how bad it is. Suppose I were to try to convince you to play this game saying, look, the range is from 2 to 12. You can't roll a 1. Therefore, there are more even numbers than odd numbers. So it's a good deal. You'll probably win money from me. But if you were to look at the whole sample space, meaning all of the possibilities, you'll notice that there are not more even numbers. It's true you can't roll a 1. But look how many even numbers there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Since there's 6 times 6 possibilities, 18 out of 36, that's 50%. So the number of even numbers and odd numbers are exactly equal. Therefore, your intuition was right. This is a bad game. Let's find out exactly how bad it is. Let's take all these possibilities and plot them in a frequency distribution table, or histogram. This means that there's only one way to get a 2, and if we get a 2, you'll win $9. There are 2 ways to get a 3, and if you get a 3, you'll lose $10. There are 3 ways to roll a 4, and if you do, you win 9, and so forth. Just by looking at this, it's hard to tell exactly if this is a good game or a bad game. So let's make things a bit more precise. Instead of the frequency, let's talk about probability. So 1 out of 36, 2 out of 36, 3 out of 36, and so forth. 7 is the most likely roll. There are 6 ways of rolling a 7 with dice. So 6 out of 36, or 1/6 chance of rolling a 7. And let's talk about the outcome. I have this function, f of x, and it works like this. If x is even, plus 9. If x is odd, minus 10, meaning you win $9 or you lose $10, depending on if x is even or odd. So there's some function that we're going to do something to x, and we're going to transform it this way. Now, the answer that we're going to get, the expected value, is going to be this equation, but let's hold off on talking about that. Let's put our outcomes right in here so we can see them very clearly. If we roll a 2, we get plus 9. There's 1/36 chance of that happening. If we roll a 3, negative 10. There's a 2 out of 36 chance of that happening. Now, what we're going to do is we're going to multiply each outcome by its probability. So this times this, this times this, this times this, this times this. And then we're going to add them together like so. So what this is saying is the expected value of f of x, not x, but f of x, is equal to the sum of the frequency of all the x's times the probability of all the x's. When I equals 1, it corresponds to the x is equal to 2. And the outcome is plus 9, so that's going to go right there. And the probability is 1 over 36, and it's going to go right there. When I equals 2, it means that the sum is 3. The outcome is negative 10. The probability is 2 divided by 36. We move all the way down the line until I equals 12, and then the outcome is plus 9, and the probability is 1 over 36. And then we add them all up. That's what this big sigma is telling us, to add everything. So if we work this all out, we get 9 times 1 over 36. That's what's going on here. Negative 10 times 2 over 36. That comes from here. 3 over 36 times 9. That comes from over here. And work all the way down the line till we get to the very end, like so. And then we add all this up together, and we get negative 0.5. What does this mean? It means that every time we throw the dice, you can expect to lose 50 cents. Not on any particular throw. The only possibilities are earning 9 or losing 10. But on average, you'll lose 50 cents each time you throw the dice. If we were to play this over and over and over again, you can guess how much you're going to lose by negative 50 cents times the number of times you play. What if we played a different game? The outcome is not plus 9 or minus 10. Instead, whatever the sum is, that's how much money you get. So if you roll a 6, you get $6. If you roll a 10, you get $10. If you roll a 2, you get $2. So f of x equals x. So I've plotted this here. Here are the outcomes on top and the probabilities here. If we work out the expected value of this game, how much are you likely to win with each throw of the dice? On average, it's 2 times 1 over 36, 3 times 2 over 36, plus 4 times 3 over 36, and so forth all the way up to 12 times 1 over 36. And if we work out the math, it turns out that the average is 7. That is, the expected value of this game is $7. Now, I don't know why I'd play this game with you, because I'd be losing a lot of money. But if we were to play this game, you can expect to win $7 with each throw. Now, what does this have to do with psychometrics? In the previous tutorial, I showed a sample that looked like this. We had 100 numbers. Here's the frequency histogram. If we were to work out the expected value of this sample, if we thought of the sample as a population, we could work out the expected value like so. We look at each bin, we look at the frequency or the probability of each bin, and we multiply the number times the probability. So the probability in this case was 1%, so negative 9 times 1% is negative 0.09. Negative 8 times its probability, 2%, gives us negative 0.16. And we go all the way to the top. 9 times 1% is 0.09. And then we add up all these products to get our expected value. So it turns out that the expected value, if we were thinking of this as a whole population, would be negative 0.41. That would be the long-term average if we were to draw repeatedly from this population. Okay, so we're thinking of this variable as a discrete variable. What about continuous variables? Do they have expected values? Well, they do, but we have to think about it in a slightly different way. Suppose we have this variable here, and I said, well, the bin width is 2. That is, we had a continuous variable, but we made it into a discrete variable like we've done in past tutorials by saying, all right, any value from negative 9 to negative 7, I'm going to call that negative 8. And any value from negative 7 to negative 5, I'm going to call that negative 6. That is, we've got intervals that are too wide, and when we plot the probability of the continuous variable falling into these bins. So we could multiply the bin, in this case negative 10, times the probability of negative 10. Negative 8 times the probability of negative 8. Negative 6 times the probability of negative 6. And we do that and add them all up and we get an expected value. But this isn't exactly the continuous variable. We had a continuous variable. We made it into a discrete variable. So we could say, well, the bin width is too wide. Let's make it narrower. Let's make it bin width of 1. So like so. And then we could do this formula again and get an expected value. But you say, wait, it's a continuous variable. It's not a discrete variable. So let's make the bin width narrower. So to 1/2 and do the same thing. So let's make it even narrower. So the bin width is 1/4 and narrower and narrower. And we could just keep going and going and going. Now, you'll notice that in order for me to get this smooth curve, I had to make my sample size larger and larger. This happens to be a sample size of about 100,000, and the bin width is fairly narrow. But you can see that the tops of these frequencies are forming a nice normal curve, like so. Now, if we were to think of the probability density function, this nice, smooth, normal curve, in essence what we're saying is that the bin width is infinitely small. You can't really divide 1 by infinity, but you know what I mean. It's a very, very, very small bin width. In other words, if you've taken the calculus class, what we're doing is we're taking x and we're multiplying it by the probability of x if the bin width is infinitely small. And we're summing from negative infinity to positive infinity. Of course, negative infinity is not depicted, neither is positive infinity, but these red lines extend out forever. So the expected value of a continuous variable is this function here. So it's basically an extension of this idea, but making the bins really, really small and the sample sizes really, really big. So the expected value is the population mean. In this case, the population mean is 0. Okay, this is a very roundabout way of talking about the mean, but it's going to be important in our next tutorial. We're going to talk about expected values and moments in the next tutorial. And you may know the moments by other names, such as variance, skew, and kurtosis.